Yeah, so good afternoon, guys. So we'll continue. I think this is the fifth session of Materials Joining Laboratory. So we have lined up a lot of interesting experiments to demonstration today. Again, one of the equipment we are going to show, you can't find anywhere in India. Okay, in this scale. I doubt, even in future, you may see anything. I'll come back to that why in subsequent, when we discuss about that. So today's class, so we are going to see two welding processes. First, we'll begin with plasma welding. Okay, so plasma welding, we use a non-consumable electrode. So it is actually derivative of gas junction arc welding. But if you look at the differences, main differences between the GTAW and plasma, GTAW we form arc, electric arc. Right? In plasma welding, we convert arc into plasma. This is by doing some trick. Those who studied in welding processes, you must already been aware how arc becomes plasma. Right? So the technique what we are going to use today to convert arc into plasma is by a physical constriction. Okay, so we use a water-cooled copper nozzle, and this nozzle constricts the arc, okay, from the envelope to promote, okay, the energy transfer between the fundamental charge carriers, so that the arc can reach the plasma state. Okay? So the energy intensity per unit area in the arc, when it becomes plasma, will be tremendous. Okay? It could be many-fold higher than when you have a simple arc in gas arc. So therefore, for a given welding the parameters, current, okay, the derived voltage or travel speed, we can increase the productivity significantly, and we can also achieve excellent depth of penetration. Okay, so in the first demonstration, so we are going to see how plasma welding is carried out in keyhole mode. Okay, so the keyhole in the sense, the power beam process, when you use laser and electron beam. So we form what is known as a keyhole. Okay, so it has a full penetration hole. So those who studied in welding material, welding processes, know what is a keyhole, right? So it is like you take an air gun, high pressure, air gun, you pressurize or you pass the high pressure air onto a water container. Water gets displaced. You can even make a true thickness hole, isn't it? So similarly, when your high power beam impinges on a metal surface, okay, you can also create, because of the various forces that are acting at the impinging location, true thickness hole. The shape of the hole is like a keyhole. Where you inside a key in a door, in the same shape you can create. The advantage of this is, we can achieve excellent penetration, full penetration weld, and we can achieve weld with extremely fast speeds. So productivity can be increased by welding thicker sections by keyhole hole, and you can also weld in autogenous without any external filler, larger thicknesses when you do keyhole hole. Okay, so the first demonstration, we are going to look few runs of high power plasma in keyhole mode. Okay, so we will be taking 6 mm, 7 mm thick plates, and you see even a single pass, even 7 mm thick plates can be penetrated fully using this. Okay, so that's the first demonstration. We will see 2-3 experiments where we'll weld in a keyhole mode or even a conduction mode. The conduction mode means we don't really fully melt through thickness. So we will just melt the top layer of, I say, 6 mm thick steel. Right. So after seeing this demonstration, we would move on to demonstration of magnetically impelled arc butt welding. Okay, magnetically impelled arc butt welding, shortly known as MIAB. The first alphabets of these 4 words. MIAB welding. So MIAB welding, it is again, those who study welding processes, we should teach, right? So it is a modification of flash butt weld. So we have 2 interfaces to be joined. Okay, we pass a current across the interface. Okay, the contact resistance It generates heat, and then subsequently we can do an upsetting in resistant upset weld. In flash butt weld, we keep some preset gap between the pipes to be welded, right? And then when we pass the current, we strike an arc between the two interfaces to be welded. So while arcing, we can also heat up the surface, and then subsequently, once the interface is heated up, we do upsetting so that the mechanical deformation can create the joint. But the problem with the flash butt is the nature of the electron path would always be along the surface, and the arcing can take place intermittently at various locations along the circumference. It won't be uniform. So in this process, okay, we keep an external magnet close to the interface to be welded. So what it does, when you pass a current with a preset gap, the external magnets, okay, arc is an electrically negative, isn't it? So when you place a magnet, the arc gets deflected or arc gets impelled because of the radial magnets we place. Arc gets impelled along the circumference with extremely high rapid speed. So we can increase the heating efficiency of the arc. Okay, so therefore we can minimize the time at which we have to pass the current. We can minimize the actual current amperage while welding, say, thicker sections. So we will show the demonstration of this MIAB welding while welding the pipes, how the MIAB welding can be carried out to weld the circular cross sections. This equipment MIAB, okay, as of now in India, if you speak, is there in IIT Madras. There is one more in WRI with small scale. Okay, the equipment what we have is the state-of-the-art MIAB facility. Why I said doing introduction will begin with, you may not even see in future anywhere, because this equipment MIAB is made in a place called Patton Welding Institute, PATON, Patton Welding Institute. It is one of the oldest welding research institutes in the world, from 1890. It is actually there in a place called Kiev in Ukraine. So you know problem in Ukraine. Okay. So, Rutgers, yeah, you have a question? Okay. So, So you see that the actual equipment we got it from Patton Welding Institute in Kiev, and as we speak, situation in Ukraine is not stable. So I just got an email. I was trying to check with my friend in Patton Welding Institute who invented this technology, Dr. Viratmi Kaczynski. Last week I was chatting with him. He felt the situation is so volatile. Those who are pro-government, okay, are in trouble. So therefore, the next few years, I don't think you may even get this equipment anywhere in India. So therefore, you keep good attention to MIAB technique and why it is very interesting and how it is actually used. And our student, Mr. Abhijit, is going to demonstrate that equipment, and he is actually developing the welding procedures for very critical applications. And because of the nature of the weld joint what we found, and we can do welding of dissimilar pipes and joints, okay, using this technique. So it becomes very interesting. So once we see MIAB welding, then we'll move back again to plasma, but not in keyhole plasma or larger diameter plasma. We'll go to microplasma. So where the plasma beam diameter can be in the order of 600 microns. Very tiny pencil beam. Okay, we can also generate by using an extremely small orifice in the water-cooled copper anodes we use. So with that, we can also weld extremely thin sections, and we can also feed a wire externally, so that we can also deposit the molten wire and droplets onto a substrate, so that we can also make that as an additive manufacturing facility. And we will see in autogenous mode how microplasma welds will look like, and we also use with the wire feeder, and then we can do that. Okay, so we lined up a series of experiments, starting with plasma, then move back to MIAB, and again go back to microplasma. and you can see all the demonstrations, and then if you have any questions, you can ask our TAs or technicians when we do that. Okay, so let's start. We go to plasma setup. Okay, yeah, good. Any questions, guys? So far? Okay, if not, we'll move, right? Good. Yeah.
Yeah, good afternoon everyone. So this is our plasma module. Right now what we are going to do here, keyhole plasma welding. We are going to join 6 mm thick sheets without doing any edge preparation. So the same plasma module we use for microplasma also. This is the plasma module. The bottom one is TIG welding source, TIG welding power source. So this shows our plasma gas 2.5 liter per minute. This shows the plasma arc amperage 6 ampere, and here it shows the transferred arc. Transferred arc in the sense of TIG welding amperage is 140 amps for welding of 6 mm thick plate. So this is our plate, what we are going to weld right now. So this is 6 mm thickness. So these two plates right now we are going to join. So see here, we are not doing any edge preparation. This is 6 mm thick. Without doing beveling itself, we are able to achieve complete penetration. So initially I will start the plasma arc. You can see the arc here. You can come and show it. My voice is not.
Pilot arc.
Yeah, this is pilot arc.
So pilot arc, what is pilot arc? Pilot arc is between the cathode is the tungsten and what is the copper nozzle. This anode. So the working is not in the contact in this circuit. Okay, so the anode is the water the copper nozzle what we use, that is the anode. So it is like independent of your system. So this is what we call as a non-transferred arc. The arc is cut between the electrode and the copper nozzle we use it to construct the arc. Okay, you see the pilot arc? That's the power. Okay, so you cannot see that. Okay, you can see how the pilot arc is like. What you see here is the pilot arc. Okay, Rajesh, go ahead. So this is 6 mm thick plate, Rajesh?
Yes sir, it's 6 mm thick.
Yeah, you see 6 mm plate with the transferred mode, you can weld it in a single part.
Now I am going to start the main arc, the transferred arc. You can see the intensity of the arc. Surya.
Yeah, you can see the effect of keyboard. The edge coming from the keyboard. Okay, so you see that at the edge, you kind of see
Okay, fine. So this is MIAB welding machine. It is known as magnetically impelled arc butt welding. So volume. Need a current. So here the principle is like magnetically impelled or butt welding. So here what we are going to do is, we know different types of joints. So here what we used to do is to butt joint. Butt joint is like this. Okay, this is how butt joint is. And here in this machine you can see this is the magnet. This is the permanent magnet of 2 Tesla power. Okay. And an arc will be forming between 2 pipes. This arc is rotated with the aid of these 2 magnets. This is the principle of this machine. So now I will explain what are the different parts which come into in this machine. One is the power source. Here we have 3 power source of maximum 600 amps. So this is 600 amps, this is 600 amps, and this is also 600 amps. And this is connected in series. So total we can get a total of 1800 amps. So this machine is capable of giving 1800 amps. So this is the power source, this is the machine, and this is the control panel. So in this control panel we can control the parameters. So let me show you some of the parameters which are the important parameters for MIAB welding. One is speed up, this is the current, this is the voltage, and these are the different stages. In this you can see that one current is like speed up current, heating current, and force-stage current. So 3 different stages if you explain here. That is one is the speed up. So one is like at 280 amps one arc will be forming, and it starts rotating. It rotates for starting we are giving 2 seconds. For 2 seconds 280 amps will be there. Then it starts rotating. So speed up it is for 2 seconds, and then heating cycle will come. For heating cycle we are giving a current of 280 amps for 12 amps. Last stage after 12 amps, so total after 2 plus 2 4, 4 plus 12 16. After 16 seconds then the force-staging will come or the upsetting will come. So the force-stage current is like 1100, that is for 1 second, and then we do upsetting for 1.5 seconds, and then forging, it will push. And the total overall time for joining this pipe is around 20 20 seconds. So this is the parameter what I am going to use to weld this pipe, which is of 57 mm outer diameter and 6 mm thickness. So here I have kept two pipes in the butt joint configuration. So this movement of these fixtures are with the aid of hydraulics.
Setting the pipe. Clamp the next component we are going to clamp. Yeah, so now you can see that two pipes almost we have kept very close, and now the parameter here also, sir, you also showing here. So now our parameter welding current and the upset pressure, everything we have set, and now we are waiting for start the process. So we have kept the two pipes, so we are going to join the two pipes. So it will be done in within a 15 seconds, I hope so. Let's start our experiment. Okay, and here we are going to switch on the power source. 1, 2 and 3. Pinhead on like that. Everything is on, right? So I will also switch on radio. Okay, so once the start button is pressed, you can observe the video of our MIAB. Please start, sir. the end you have got an offset. Okay. Yeah. Yeah, so welding of two pipes have been completed. So this is for our joining of our two pipes with MIAB, magnetically equal arc welding. And you can see the graph also. So whatever we have set the parameters, so it will be available in the form of graph. Right. So here it shows the red color is the one. Okay.
So here red color is the current amperage and blue is the voltage what you have given, like 20, 24, 24, 25, and these are the different stages and the time. And I have set 300 for the starting stage, and again 280 for starting stage. You can see 300, it will be fluctuating a little bit, and 280 for the heating cycle, and 1100 in the last stage for upsetting for the 4-stage current. So this is the total time schedule for this MIAB welding. Total it has taken 20 seconds to complete the welding.
Okay, so this is what about the MIAB welding process. In MIAB we can do joining of pipe to pipe. Solid is not possible. So solid is possible, but rod also possible. You can see the rod. So you can join solid rod also.
25 mm.
35 mm.
25.
1 inch rod. 1 inch rod. But this machine is capable of going up to 75 mm outer diameter. From 1 inch to 75 mm diameter, up to 1 inch to 3 inches maximum we can go with our MIAB machine, joining of two pipes. So, any no, actually you can see close, bring close. We have a job can be kept this much bigger pipe we need. We need about more than a feet we need, but we are joining a very smaller pipe, so that will fit into one grip, so that with one grip you will not have the gripness. So for that we need an additional, that is a backing rod we are keeping to have more gripness, because we are giving an 70 how much is the pressure? Upset pressure, how much? 80 psi. 80. See, the upset pressure what we are giving, it is 80 psi. Okay, so 80 psi we are giving, so that and again there is a limitation. So the upset pressure, the holding, the sample holding pressure should be higher than our upset pressure. So when I do an upset, it should not push away. So that is also that. So that is done by means of an hydraulic unit. We have a small hydraulic unit which is attached with this machine. So that's why I hope I have answered your question. Nothing but backing rod we are keeping. That is not to be joined. You can see here, these two pipes we have joined. These two are kept for our backing purpose. And what we do, we cut the portion here cut the portion here, and we will take this for our further characterization study. Okay? Yeah, but in magnetically in this MIAB, as of now we are joining only the steel pipes. We have not tried with the dissimilar alloys. Dissimilar alloys, that is an Ukraine. This machine is supplied by the Ukraine. If you see the machine, the construction of this machine is really very simple. Okay, they have supplied three welding power source, and each power source has to service. Said that each power source has got a 600 amps, and if you add it up to 3, it will come to 1800 amps this machine can supply. And of course they have given a very small hydraulic unit also for moving our movement of our the one sample. For that they have given, and simple the electronic devices they have given. With that the whole machine had come as an MIAB. Okay, and of course we are the institute as well as on our MJ lab or a joining additive manufacturing lab proud to have this machine. In India no one is having other than WM. And this particularly this MIAB is a production equipment. So we can take this to a field and we can use for a production also. That is the beauty of this machine.
Joining Kangan sir. So this is mostly to help for laying of the pipes. If you see for pipelines, they will be laying the pipes kilometers and kilometers. So
In the
after
field.
it's like in the field. So it is like some 30 meters. After 30 meters we have to join it, right? So we can use this machine there. We can join easily. Within 20 seconds we'll join this blade. Otherwise, if you see for joining these kinds of pipes using a filler, when it takes like 30 to 40, mostly 1 hour it will take to join 6 mm thickness pipes. So the advantage of this machine is like in 20 seconds you can get a weld. And this will be so your the time for laying this many kilometers of pipe can be reduced. This is the advantage of this machine and this processor.
Yeah, thank you. And in fact, we have two equipments. Like earlier also we had a flash cut welding machine that consumes around like 150 kVA. It is almost a substation, I should say that. But we have discarded that machine, and luckily we got this machine, and now we are in a position to demonstrate as well as take up the research with this MIAB. Okay? Shall we move on to other experiment? Yeah. No, that is a 1 inch diameter. Okay. So we have a different grips. Sorry. Different attachments we have. So we will magnet. Just leave it. So we will keep this for smaller diameter rod. We keep these adapters on top of it so that we can do our 1 inch pipe also. So if we have a bigger diameter, so likewise we have a different adapters. So we will keep all that and we will be joining the different rods and pipes. Rods and pipes, both we can do it. Only thing for rod, you may need a very high current and very high upset also, because the whole surface has to be, the current has to be passed into that. And also the thickness of the pipe is also very important. So minimum thickness you can use 3 mm.
3 to 6.
Okay, 3 to 4 mm or 3 to 5 mm we need. If it is going to be less than 3 mm, the clamping pressure itself will crush your tube itself. So we cannot join that. Okay. Thank you. So I would like to say special thanks to Mr. Abhijit, who is doing research in one of his chapter is with the MIAB equipment. Using MIAB equipment, he is joining of different materials. And thank you, Abhijit. Thank you. So let's move on to our plasma arc welding. So and then arc welding, you can see nicely Mr. Rajesh has buffed this material. So this is what about our first experiment where we are seeing. And another experiment we are going to see with the same. Okay. So now let's move on to our microplasma. So we have very nice plasma. We are going to use 10,000. Okay. So I
Like this. Yeah, hi, good afternoon everyone. I'm going to just give again a brief about the plasma welding process. Plasma welding process, which is very similar to TIG welding process in terms of ignition and construction wise. Even for ignition wise, it also has high frequency ignition only we will do for plasma as well as TIG. In terms of construction wise, if you see, it has additional water cooled nozzle setup when compared with the TIG welding process. And also here in this plasma welding process, we will not see the electrode outside, which is not exposed outside. There, which will be inside the nozzle. These two will contribute for the construction of arc, which will help to get kind of a beam welding arrangements. So we will see the machine setups, and this is for non-transferred setup, and this is for transferred one. Here it has two gases. One is for shielding, one is for plasma generation. You can see this is for plasma generation gas, and bottom this is for shielding gas. And whatever we said here, this is for non-transfer. So I said for the plasma generation of 0.3 liter per minute and amps for 4 amps. We cannot go beyond certain limits, which is restricted based on the nozzle which we are using. And here this is for transferred one. Here based on the optimum trials, I'm using 15, and voltage will display only during the welding process. Okay, we'll go and see the machine. Based on the current, we can classify the plasma into 3 types. One is microplasma, another one conduction mode, another one keyhole mode. Earlier you have seen conduction and keyhole mode by Rajesh. Now we are going to see the microplasma. Microplasma set process the current range which we are using in the range of 1 amps to 35 amps. Even we can go below 1 amps based on the power source. What we are having here is we can go from 1 amps to 35 amps. So what you are seeing is,
can I interrupt?
yeah, sure.
Hello students. I want to add up to Mr. Prakash. This microplasma equipment was indigenously developed by our own alumnus. So they all having an AMTDC called an AMTDC. They have an production as well as a research setup at our research park. So they have helped us for making this microplasma. And the beauty of this microplasma is it is a CNC program. Where it is a 3-axis machine or 4-axis machine. So it is an highly appreciable equipment. And from this microplasma, we have got 4 or 5 journals out of it, and it is a very good journal. So that's what you are going to see our demonstration of our microplasma equipment. So please.
Thank you for pointing out this CNC table. Yeah, this is in-house made CNC table, especially for this microplasma setup, which is a 4-axis table, X, Y, Z and A. Here you can see this is a rotating table, X, Y, I'll show. You can see X and similarly for Y and Z. Rotation is also possible, but now I have given the clamp, so you can just see it is also possible to rotate. And the distance which we can move is 200 mm X, 200 mm Y, similarly 150 mm Z. And this machine, the speed, if you see, we can run 10 mm per minute to 5000 mm per minute travel speed we can achieve using this machine. And also we can change the filler diameter size from 0.2 mm to 1.6 mm by changing the rollers. So for today's experiment, we are going to show 3 demonstrations, 2 autogeneous one and 1 with filler deposition. So now whatever you are seeing, this is called non-transferred arc or pilot arc. This non-transferred mode, which means the connection or the circuit is between the electrode as well as the water cooled nozzle. This inside itself a water cooled nozzle, and inside one electrode will be there. That is non-transferred one. Transferred means during the welding process, the circuit is between the electrode and this substrate by using this ground setup. So we'll show a demonstration now. Okay, I'm going to start the process. No, what to do is second one. I will use the current and I will. filler deposition. Earlier we have seen two autogeneous mode. Now we are going to see with filler depositions.
Slowly.
You can see here, this one is autogeneous one, and this one is with filler depositions. The main advantages of this microplasma is we can even fill very thin sheets, even like files also we can use. In automobiles, aerospace, and nuclear applications, like for building up bellows and diaphragms, we can go for this microplasma welding process when compared with other process. And one other advantage is the arc stability will be very good when compared with other process like even TIG because of arc constrictions. I will open this nozzle and I will show you how the electrodes are kept inside. It is way inside the nozzle. Shall I show it, sir?
Yeah.
Non-transferred arc, where the connection is between only the electrode as well as the palpable nozzle. So irrespective of the material, we can use this pilot arc to weld, or even for cutting also we can use. Generally for wire mesh are available, right sir? For cutting the wire mesh we will use this pilot arc one. Even for welding of bellows, small bellows with the diaphragms, we can use this pilot arc. That's the advantage. And one more thing, the heat input will be very less in non-transfer when compared to the transfer.
But by any means that we can use it for a spray coating kind of technique.
Yeah, even for plasma spray coating, they will use this other setup, which is little bit, the nozzle wise design will be different when compared to this one. But here we won't use any spray type coating setup.
Okay. Thank you, sir.
This is the ceramic cup, and this is the nozzle which we are using, which is 1.2 mm diameter. Even you cannot see the electrode outside of this nozzle.
Ceramic material. So you show this. This is the one, the plasma arc welding nozzle. Okay, you can see the bend. Whereas in TIG welding you have got straight. So that is why in TIG welding the tungsten electrode will come out, whereas in plasma arc welding it will be inside. So that is why Mr. Prakash mentioning that the arc will be constricted. So arc is when you are constricting, you will get more power. So for plasma arc welding or a TIG welding, we use both the power sources are going to be the same. whereas only the design of nozzle only will changes. Okay, so please continue, sir.
Yeah, here this is the tungsten electrode. This is the nozzle. This is the copper cooled nozzle which is set up to cool the nozzles. So if I keep this on, the electrode won't come outside. You can see here. When compared with TIG and all, you can directly see the electrode will be outside, but here it will be inside to constrict the arc.
Is this positive or negative?
This is positive.
Positive.
This is cathode and this is anode.
Right. So, electrically speaking, students, here we have two positive. One positive here, another positive here. So, inside we have an, since we have a positive and electrode, that's how the pilot arc is ignited. Okay, so you please see here, we have two electrodes. One inside we have one more a negative, and outside also we have a negative. So inside whatever we have a negative positive, with that it creates a pilot arc. When I go close to the material, that arc will be get transferred by this negative. That negative will be getting disconnected. This is how the pilot arc and the transferred arc. So, students, any questions, please let me know. We have another vegetable, we have attached. Ajay sir.
It all over.
All the na? Okay. Right. So, students, with this we are coming into end of our lab class. Any questions, please ask us right now. If you are able to answer, it will be good. Because our Professor Morgan has gone for some other meeting also. So please let us know. So, and about the processes, we are able to answer questions. Students? You are there? Hello? I am audible. Listening? Okay, okay. Otherwise, I will ask the question. So, we have observed, sir? Yeah, please. Yes, sir. Exactly. See, TIG welding normally will have a tungsten it is a non-consumable welding process. So we always give negative to the tungsten, that is the electrode, and positive to the base material we normally give in TIG welding or a plasma arc welding. Okay. So whereas in the manual metal arc welding, it is going to be a reverse product. Okay, so and one thing I have observed from Mr. Prakash that the main purpose of plasma arc welding have to be used application. Hello? Exactly. Exactly. So for thinner sheets, we are going for the microplasma. That is the difference. And of course, above the plasma welding process, we have a laser beam as well as an electron beam welding. So these are all the welding process. Normally we say it is a keyhole welding process. So in that line, plasma is also coming in. Okay? Right? So shall we suppose? Okay. Okay, students, so this is what about our today's lab class. So next week we are going to see the solid state welding process, friction welding, friction stir process. So I thought of having a MIAB also into the solid state welding process, but we have a friction stir welding. Sir said that we can have a friction stir welding as a separate day for our practical sessions. So next week we will be going to have a friction stir welding process. So please, and I would like to say special thanks to Mr. Rajesh and Mr. Prakash and Mr. Jack Pravesh and Mr. Diveta and Mr. Surya Kumar sir and Mr. Surya. So, and I would like to say special thanks to Mr. Abhijit, who had all the way come for our MIAB operating of MIAB welding equipment. So of course I should not forget to say thanks to Professor Murugan also, and of course you are all the last one to say special thanks to me. Thanks to be here, pleasant listening in the online welding lab. So thank you students, see you next week. Thank you. Hope you can, before the next lab class schedule, kindly submit your lab report.